Hi, everybody. Welcome back to Dave's Math channel. This is my continuing feature on the Math Lovers book, three-volume series I wrote from 2019 to 2022. And it's available in both Kindle and paperback format on Amazon.com in case you're interested in purchasing any combination of these three volumes. Little plug for my book. Anyway, I'm up to chapter 9 of volume 1. I'm starting a new chapter. This is on dynamical systems and chaos. And this is a very important math topic. It's a pretty new one, too. I wouldn't say the theory was really developed very much until probably the 1970s. One reason is because a lot of it requires computer simulations, very complicated math to analyze. But a lot of progress has been made during the computer age on this area of math, and also relates to something called fractals, which I'll get to in chapter 10, which I think is a really exciting area of math. So today I'm just going to give you kind of a brief overview of what dynamical systems and chaos is all about. I go through it in my book. I'm not going to bother with this slide, but this is just the intro I give in my book explaining, what dynamical systems and chaos are all about. Um, when they say pictures worth 1,000 words, so I think it's probably better if I just show you some pictures. So here's this diagram shows you the different kinds of behavior you can get from dynamical systems. And first, I think I should tell you what a dynamical system is. So a dynamical system is a system that evolves with time. You start in some initial state. A good example is the weather. I mean, with the weather, you've got certain conditions on the atmosphere at various times, and depending on how the wind's blowing, or how much the atmosphere is warming up, or if there's storms coming in, the weather changes from minute to minute, and it's a very good example of a dynamical system. And we have developed models of the weather that kind of predict it, at least for a short period of time. I think we can predict the weather pretty accurately right now, up to about a week in advance. That's why weather forecasts are pretty reliable for the next 5 or 6 days. Beyond that, there's something called the butterfly effect that prevents you from calculating what's going to happen in the distant future. That's kind of a property of dynamical system. That's what's called chaos, by the way. That's where the name chaos comes from. Even though the initial conditions can be specified, as precisely as you want, you get kind of an exponential growth in uncertainties, and that means after a short amount of time, you can't predict what's going to happen. But anyway, there's different types of dynamic behavior of dynamical systems. This picture shows continuous dynamical systems, and you kind of see this parabola in the middle of the picture. Everything inside this parabola is stable. Um, so you get both stable and unstable equilibria in dynamical systems. I guess the line in the middle, the vertical axis, the y-axis, is where it kind of oscillates. But then when you get outside of this parabola, you're in an unstable region, where things blow up. That's where it's really unpredictable, when things diverge. If they converge, you converge to what's called a source, or sink rather. Um, otherwise you emerge out of the source. So, and then there's kind of intermediate states. So if you look at the x-axis, the horizontal axis, this is where you have lines of stable fixed points. This is sort of an intermediate case. So in the bottom half of the y-axis is 2. You get these things called saddle points. They're stable in one direction, but they're unstable in a orthogonal direction. So these are just the different kinds of behavior you can get from dynamical systems. Um, and there's a lot of good examples of dynamical systems. I'm going to get into all these in chapters 9 and 10. I think this is a really interesting one. This picture here is what's called a bifurcation diagram. And this comes from the logistic equation. It's a very simple equation. I think one thing that's really fascinating to me about dynamical systems is you can start with a very simple equation, but it's nonlinear. That's why it's hard to predict what's going to happen. So for the case of the logistic equation, it's a very simple equation. Just x goes to rx times 1 minus x. You start with some initial value of x between 0 and 1, and then you let r be some fixed constant between 0 and 4. And depending on the value of r, you can get different behavior. If r is less than 1, you get it always approaches 0. This is the example of a source, like the inside of the parabola here. But then when r is between 1 and 3, it's still stable, but it doesn't approach 0 anymore. It approaches a non-zero value. And then if you go beyond 3, then you get what's something called bifurcation. If you notice between about 3 and 3.5, there's a sort of a fork where there's two equilibria. That means it oscillates between one and the other. And then beyond 2, you have 4, and then you have 8. You get doubling for a long time, and then finally you reach a point, I think R about 3.57, where you go into what's called the chaotic region, where it no longer even oscillates, it's just kind of random. I mean, it is at least in theory predictable, but like I said, because of the butterfly effect, you have to kind of run it a simulation 100 times or 1,000 times. There's no other way you can predict what's going to happen to it. So I think this is a really nice picture. Um, and uh, um, and I was mentioning the butterfly effect. This picture almost looks kind of like a butterfly. This is a picture you'll see a lot. This actually comes from a model of the weather. I think this fractal set was first discovered by a very famous mathematician who studied dynamical systems. His name was Lorenz, not to be confused with Lorentz, who was turn of the 20th century, came up with Lorentz transformation, a lot of stuff involved in theory of relativity. This was a different guy. His name's spelled a little different too, Lorenz, and he lived a lot later. I think he first came up with a weather model in 1960. At that time, there weren't very good computers, so his model wasn't really practical to model on the computer yet. But as computers became more advanced, it became more and more practical to do so. And this picture you see here, this is kind of typical of chaotic systems. This is the attractor set you get for the weather. It's not a point, so it's not really a stable equilibrium. But what happens is you always end up on this kind of funny looking butterfly region. But once you're in the butterfly region, there's kind of no way you can predict what's going to happen because you get divergence. I mean, if you're on this left spiral, you can see the parts of the left spiral that kind of end up in the right spiral. The left spiral is El Nino. These are different weather patterns. El Nino is kind of a storm pattern where you get a lot of rain, and La Nina is kind of the opposite. You don't get much rain. And we experience these in California a lot. I used to live in California. We'd have some El Nino years and some La Nina years. And anyway, this is kind of the set that describes what's going on. So that's kind of a practical application of dynamical systems. And then I think you guys are probably familiar with a Mandelbrot set. I think this is really, really fascinating. And by the way, the Mandelbrot set, it's a complex valued set. And it's actually a kind of it's a continuation of the logistic equation into the complex domain. I showed you the bifurcation diagram for the logistic equation. This is for R going from 0 to 4, but for the Mandelbrot set R, or they usually call it, I think they give it a different name, Z naught or A, but it can be complex value. And and you get really, really, and it's funny because this is another example of a set that's governed by a very, very simple equation. Just z goes to z squared plus c. Yeah, they call it c actually. So c is an arbitrary complex number. You start z naught equals c, and then zn plus 1 equals zn squared plus c. So you square the last value when you add this constant c, and you keep going. And for some values of c, this process converges. Those are what are called points inside the Mandelbrot set. That's a black region. Actually, this is a region within the Mandelbrot set. The entire Mandelbrot set looks pretty much like this, but this is kind of a mini version of the Mandelbrot set within the big Mandelbrot set. And this is a typical, the Mandelbrot set was called a fractal set. And this is very typical for fractals. Fractals tend to have the same structures on all distance scales. As a matter of fact, that's one way you can define a fractal. And this Mandelbrot set is amazing to me because for such a simple equation, it has some of the most complex behavior you can imagine. And, it's still a very active area of research. Also gives you really beautiful pictures like this one. And there's one other thing. Dynamical systems don't have to be continuous. They can be discrete. And a good example of that is Conway's Game of Life. I'm sure a lot of you guys are probably familiar with this. I used to play this simulation a lot. It's what's known as a cellular automaton. There's actually a lot of these that are known now, but Conway's Game of Life, I think, is the most famous one. This is a computer simulation. Again, very, very simple rules. There's four rules that govern this game. I'm not going to say what they are, but it's a grid of it's a square grid, 2 by 2 square grid, and you have these little square cells that are either off or on. I guess the ones that are on are shown in black, the ones that are off are shown in white here. And this is another dynamical system. The rules kind of tell you how this system evolves. And it has amazingly complex behavior for such a simple system. I love this thing. And I actually do talk about Conway's Game of Life, either in this chapter or the next chapter. So you will see me go into this game in detail. And I think I'll just say one more thing about this. John Horton Conway, he was a very famous mathematician. I think he died a couple of years ago, but he, um, he did a lot of important work in math, and I think the thing he's most well known for was his Game of Life. Even though he wasn't really proud of this, he got really sick of it because he got like thousands of fans asking about the Game of Life all the time, and I don't think he liked the fact that it was called Conway's Game of Life. And I really think the main reason it was known as that was because there was a Milton Bradley game called The Game of Life. You guys are probably familiar with it. I used to play it with my sister as a kid. And I think if he had just called this thing The Game of Life, I think a lot of people would have thought they were talking about the Milton Bradley game, even though they have very little to do with each other. But anyway, so that's just an overview of dynamical systems, which I think is a really fascinating area of math. Anyway, that completes my video for today. Thank you for watching. Long live math, and I'll see you guys next time. Bye.